Hello, everyone. Thank you for joining today. Welcome. We'll just wait for the customary couple of minutes so that everybody can join here. Yeah, I see more people joining the Discord chat. Yes, please join the Discord channel that you might have received the invitation link in your registration email. We'll be using the Discord chat to chat today because the Zoom chat is not super great for that kind of usage. Yes. Oh, can you not hear me? I should be, yeah, you should be able to hear me. Okay. Perfect. Thank you for, hello everyone. Hi, username. Okay, let's get you a minute to sort your audio out. I hear more people coming in. Yeah, one more minute, I guess. Who's still joining? Okay, people still joining. Yay. Okay, there we go. Perfect. Okay. If everyone can hear me well, then I think we should get started now. There we go. Okay. So yeah, it's past 3. I guess we'll get started. All right. Okay, let's go. So welcome everyone, and thank you so much for joining today. I'm super glad that we'll get to talk about the product that we sell a little bit more. And we're here to answer all the questions that you might have about the product. So you see, we have a Discord chat. We have people there also, which will help me answer questions if I'm a little overwhelmed. And yeah, this is going to be interesting today. You'll get to sit back and relax and enjoy a demo of the product. So again, thank you for your time. Yeah, I hope by the end of the hour you'll get a better idea of what the product is. I hear people joining, so again, please don't join the Discord chat as soon as you can. We will be taking questions there if you have any. Okay, so to start today, just a quick word about the company. Tetrane, we've been there for about 10 years, and we're the software editor of REVEN. So REVEN is the name of the product, and Tetrane is the name of the company. It's a reverse engineering framework for doing timeless analysis. So we'll talk about that today. And we are based in the USA and in France, and most of the development happens here in France. Of course, customary introduction. Will be your host today. My name is Matthew. I'm an R&D engineer at Tetrane, and so I spend like half my time working on the product and half my time being with prospects, with clients, customers, and doing labs, trainings, or presentations like today. So I'm kind of halfway between customers and engineers. You can reach out to me via email, Twitter, or whatever other means that you might want. But I'm not alone today, certainly not. On the Discord chat, we have at least 2 people from Tetrane. We have Mark, he's our CEO. So if you have any business question, here's your guy. And we also have Quentin, which is one of my fellow engineers, and he'll help me answer questions if I miss any, or if he has more details, more technical details than I do on the subject, he'll help me out answer questions. So if you do have questions, please post them on the chat. I'm monitoring it on that screen, so I'll be able to answer questions and take them as they come. and if not, then I'll have tech support there. So for those people who might have joined in the past minute, please join the Discord chat. Yeah, we won't be using the Zoom chat today. Please join Discord. You don't need an account. Just enter a username and that should be enough. About the lab. So if you're here, you might have heard about REVEN. Might be the reason why you're here. So we split that lab into 2 different sessions. Today we'll be having a 1-hour session in which I'll be giving you a tour of the product, a demonstration about what timeless analysis is, what REVEN does, about how you can record a trace. So, going from the very beginning to the very end of your analysis, and what are the product's feature, how they're meant to be used, what are the use cases. So we won't cover all possible use cases because this is more of a framework than anything. But there are key use cases that we think about when we present the product, and that's what we go through. We also talk about integration with third-party tools because that's really important. And if we have time, we might talk about more advanced and slightly edge, advanced use cases that you might think about. So today you'll get to enjoy and relax and sit back and watch the demo. And next week, though, we'll have a 2-hour workshop where you'll get access to the product for real. You won't be. We will give you exercises on pre-recorded traces, and through these exercises, you'll get to get your hands dirty and start using the product, learn about the product, and even we'll work on a real CVE in the kernel. So by the end of the workshop, we'll have actual results about a CVE, which is something kind of nice, and we'll do things that are really specific to REVEN there. So it's going to be a pretty interesting workshop as well to get started with the product and to get excited about what you can do with it. So yeah, 2 different sessions, 2 different but complementary objectives. And today we'll just sit back and work through the demos and what you can do with the product. Again, for the people who might have joined, we have a chat. Please on the Discord, please post your questions there if you have any. Okay, timeless debugging. REVEN is a timeless and debugging and analysis framework. So what is first timeless debugging? You may have heard of it. There are other tools on the market which do timeless debugging. WinTDD is one of the most known one. The idea is that instead of debugging something live while it's running, you'll get to record a trace of the thing you want to analyze, and then you will work either forward or backward in that trace. So let's say you reach an interesting point and you have a question about why you're there. You're able to step backwards in your trace and get answers about what happened in the past. There are many use cases where this is super interesting because, it might be hard to go back. It's always hard to go back in the past, of course, but also because sometimes you might have addresses that change, or when you restart your process, or maybe your bug is not super deterministic and it's hard to reproduce multiple times in a row, or make many kind of different use cases like that you might want a trace for, because then once your trace is recorded, it's fixed and everything stays there and you can take your time and work on it. So obviously there are many use cases like that where timeless debugging is super important. REVEN does timeless debugging on a virtual machine. So not just on process, but on the entire virtual machine. And that means that we have huge traces. And at any point in that trace, you can access the entire set of the virtual machine. It's really like God mode. So we don't care about whether it's in user land or kernel land. We'll be able to see it, and we get access to everything. But of course, that's a lot of information, and that might be hard to work with. So on top of the trace, we provide tools, and that's what we tend to call timeless analysis, because really there are tools on top of the trace to help you work with it. Examples include we compute the history of accesses of any piece of memory that in the trace. So anytime you see an address, you're able to double click there and see everything that happened on that particular location during the trace. So it's super easy to go back to the previous write or stuff like that and get answers, precise answer about what's happening. We also have something like called data tainting, which is a way to track the data flow throughout the trace, and it's going to help you locate things super easily. So basically having those tools on top of that, having that huge amount of data and tools on top of it, you're able to extract a lot of information super quickly. That's the goal of REVEN there. So that's for the analysis part. And of course, there's a workflow because you need to recall that trace. So we made sure that the entire workflow is covered with REVEN. You get a way to record, manage your virtual machine, record scenarios, create a proper environment and setup for the thing that you want to record, maybe a certain version of Windows, a certain DLL, all of that. So you get first to record your trace. This is you create the exact setup that you need, you reproduce the thing you want to record, and boom, you have your recordings. Then there's a second phase called the generation phase, where we automatically process that trace and extract indexes and a lot of data from there. And the idea is that once that's automatic, that could take up to between a minute to a few hours, depending on how big your trace is going to be. And once you have that, you get to analyze your trace either through the GUI, and since we have indexes, it's super fast to seek inside your trace, go to the beginning to the end, doesn't matter, everything is indexed, so it's super fast. And so either through the GUI that we provide or automatically through the Python API. And most data is accessible through both means in the same way. So it's really easy to go from one to the other because the concepts are the same. And you can either, your workflow might be focused on interactive, but the Python API might help you filter things out a bit more than the GUI does. Or your workflow may be mostly automated, but you might need a little bit of interaction to just get to the interesting point. You can combine the two very easily. The concepts are the same. And last but not least, we realized that REVEN is one tool in the toolbox, and it helps you get some answers, but not everything. And there are other tools there, of course, IDA and WinDebug for those of you for Windows, or also Wireshark for when you're talking about network, volatility, other tools like that are super interesting, provide a lot of features. And we made sure that when it makes sense, we can integrate with those tools. So you can sync IDA, you can connect WinDebug to a trace, we'll see that. So you can exploit these tools features on top of a trace. Okay, so that's a whole workflow of REVEN. And so I mentioned the Python API for the analysis part, but you can also automate the recording phase. So it means that if you have a further tool chain and that generates crashes and you would like to have recordings of those crashes, then you can plug REVEN after your further. And this is a valid use case that we support, and you can generate traces automatically and then either do an automated analysis on that trace or just give interactive access to the trace to the analyst that might use it. Yeah, I mentioned IDA all the time. Thank you, Mark. It also works on Ghidra. This is super important. We won't see it in my demonstration, but we make use of an open source plugin that that supports Ghidra as well. Very important these days. Yeah. Yeah, analysis automation. This is what I mentioned. You can automatically push something, create a scenario. It will spawn the virtual machine, push the files automatically, all of that. The replay will be automated, and you can also have an automated analysis if you're so inclined. Okay, are there questions so far? I'll give you a second if you have questions. Otherwise, I'll switch over to the demo part. I'll start with a demo of the recording phase. So I'll show you what I'm going to access then during the analysis, but I'll show you how I record it. And yeah, we'll start looking at what this whole means, and we'll start doing the taint and all of that. Okay, I see no questions, so I'll move forward. All right, what do we have here? So the screen is not perfect. So the thing we're looking at right now is the project manager. This is REVEN's UI where you will manage your virtual machines, your projects, so you can create or set up and manage your data basically. So what I have here is on this machine I have a single virtual machine which is configured for my demos, and have a series of snapshots for that virtual machine that I can use with different setups, which I can use. And the thing we're going to record is a crash in the kernel, which generates a blue screen. And we'll see how we can analyze that. So let's do that recording. So first I'll head over to the scenario manager, create a new scenario for you, and specify which virtual machine I'm interested in. And I'll upload the proof of concept in question that I'm interested in, and just restore a snapshot of a virtual machine which I know is vulnerable to that proof of concept. That's what I have there. And push the CD-ROM. So I selected the file I wanted to upload to the virtual machine, and by default we'll create an ISO file for that and push that to the virtual machine. We found that's a very reliable way to push files no matter what the configuration of the VM is. We don't need network, we don't need anything. CD-ROM is hot swappable, so that's really easy to use. So I pushed that file to the VM, and now I'm going to open the Explorer to access that file and do a manipulation of that file, which I know will generate the crash. One important thing to note here, you might notice that the virtual machine is acting a little slowly. That's because we are running the virtual machines here in emulation mode. While we record machines, they are not running hypervised, which is the usual way of running virtual machines, but in this case they are emulated. This is one of the two ways we have to record scenarios. That's the most effective and most reliable way. This means there are a lot of things we can do. So it's a very interesting way to do recordings. And as you can see, still the machine is very usable, and it will allow me to do what I want. So I'm not going to do the manipulation that's going to crash the system just yet. Before I do that, I'll press the Start Record button. Once I press that, everything I do in the virtual machine is going to be recorded. Nothing that prior to that, but everything after that. So what I'm going to do is press Start Record, do something on the machine to crash it, and then stop the recording. Okay, so let's do that. I'll press Start Record. I'll do a manipulation. Yeah, my system crashes, and I stop the recording. So you see it was kind of quick. I recorded a couple of seconds there, but I have everything I need. And I mostly don't have things I don't need. So I can either record something manually like I just did, or we have other more elaborate ways to do recordings, like you can control the recording from within the guest, you can control the recording from the outside, we can record processes automatically when they crash. We have a lot of ways to make your recording easier and closer to exactly what it is you want to record. But for now, let's just do that thing manually. I have a question on the chat. VM also runs with TCG disabled. I'm not sure. I see Quentin is typing. I'm not sure what you mean by TCG disabled. They do run with TCG, yeah. Yeah, exactly. That's it. You don't see it here because I'm recording things, but you can use KVM to configure your virtual machine. That's very important, and that's a very interesting question. And when you install your virtual machine or install software, install Chrome or whatever it is you want, you can boot the machine in virtualized mode, so it's regular speed, and you do your installation there, and then you shut it down and restart it in emulation mode, and that's the thing you can record. So that's the only moment where we need the machine to run in TCG mode, because this is the vocabulary for QEMU. TCG mode is fully emulated. So now I have a recording, and if I commit it, I can then move on to the next phase, which is the index generation phase that I was telling you about. It's probably going to take a minute here, so I'm not necessarily going to replay it here because I already have the same trace replayed somewhere else. But for a trace like that, it would probably take about maybe anywhere between 1 or 5 minutes. Yeah, Quentin says in REVEN you can also record using VirtualBox, and it's not in emulated mode. Yeah, that's the second mode of recordings. if you have questions about details there, feel free to continue asking them. But otherwise, I'll move forward with the demo there. Okay, so let's say I did the replay. So I created all the indexes. Okay, thank you. I created all the indexes, and what I get in the end is this. So this is the GUI for analyzing my trace. And what I have in the middle is not the same view that you would get with a regular disassembler, because instead of focusing on a binary, what we do here is list all of the instructions that the CPU executed during the trace. So moving down like this, I'm actually moving forward in time. And when I move up, I'm moving backward in time. And when there's a jump, the next instruction is the destination of that jump. You see, this is A21, this is A21. So what I have here is really a trace of execution, no matter what the current binary is, no matter what the current process is. We'll see that jump from binary to binary. When I have a call, the next instruction is going to be the destination of that call. So that calls actually KI interrupts of dispatch something. So it's really different from what you get from a regular disassembler where I guess instructions are sorted by address. Here they are sorted by time of execution. And the numbers we have here are our timestamps. We call that transition numbers, but really they are a representation of time. So you have a trace, and you saw me clicking around, and widgets around that got refreshed because they represent the state of the VM at the moment that I selected. So we have a backtrace, which is the stack trace mostly, and you see it's mostly unknown because I'm at the very beginning of my trace, so I don't exactly know what called me, although I have hints. We also view the CPU registers for what makes sense for the CPU right now. I can view any location in memory that is mapped. And I can also look at the frame buffer, because the frame buffer is just a region in memory. So instead of displaying hex numbers, we display pixels, but that's the same thing. That's just a view of memory. At the bottom, what we see here is the timeline. We'll push search results, or we'll also push bookmarks, little icons here. But I can also use it to basically seek in my trace as if it was VLC. And by doing that and looking at the frame buffer, you'll be able to see what it is I recorded for that trace. And yeah, okay, what is I recorded there? And you see that I did exactly the same thing as I did a minute ago. So I'm moving forward. You see my mouse moved. I got ready. I got close to the file. And when it's trying to display the tooltip, then I enter the blue screen. And then we have the details of the blue screen. So basically most of that trace is useless to me because this is the execution of the blue screen and my crash is way earlier. But we do have everything. And if we were to zoom in at the moment where I'm painting a glyph on the screen, we would see the details of the glyph, being displayed line by line. We do see absolutely everything there. Okay, so that's my trace. This one is about 200 million instructions. So that's not a very big trace by REVEN standard. That's decent, but that's not very big. We could go up to billions or tens of billions of 10 billion instruction is already a pretty nifty trace. But still, we can handle quite a lot of instructions, and the UI will stay snappy, and all the algorithms are meant for that kind of scale. But that's a lot of information, and I can't necessarily look into from the outside just like that. So I need tools. So first of all, let's locate our crash and have a look at it, and then we'll use these tools, because right now what I'm doing is really timeless debugging. I'll try to locate my crash. So if you're used to WinDebug, when you have a crash, the OS gives you WinDebug gives you control at a certain point in time, and basically one of the symbols that gets called every time there's a blue screen is KEBug check. So the equivalent there of having a breakpoint on the BSOD is going to the KEBug check. That's there, and I can at that point I do have the usual, although it might be here. yeah, if you look at the arguments, you would get the common codes that you would get to explain what the crash is all about. But here I don't necessarily need that because I have the backtrace and I can use it to move backward in time. So when I double click somewhere, it takes me to the call. I can use that to see why I am here. What function decided to call to trigger a blue screen, and that's so the access fault comes from a page fault, and that page fault is inside the mem copy. So there I have a memory address that I can't dereference, and that ultimately causes a crash. So that's exactly where my crash is, in NTOS kernel.exe. So I didn't have to do anything fancy here. Just moved back the backtrace and I located my crash, because most of that trace is just, the blue screen executing. Another way to have done that would have been to search from inside my trace. That would be the equivalent of setting a breakpoint, if you will. So if I look for NTOS kernel and say ke bug check hex, like that, I do have a result here, which is presented in the timeline. So if I click next, boom, it goes to the result, and then doing the same thing, I can locate my crash. I'm sparing you the details here, but basically what we have there is we have an offset. We have an address and an offset in that buffer, and we are accessing that. And in that case, the buffer is too small. Okay, so we have an offset that we have an out of bound memory access, and that's my crash. The question is, why do I have that offset? We are going to assume that the address is right and the allocation of the address, the allocation of the buffer is right, and really what's wrong here is our offset. But that's one hypothesis we'll start with, and that's the right one. But it's easy enough to validate the other, like trace the allocation and find the allocation and find the arguments to that, and verify the soundness of all that. And that's something we'll get to do during next week's workshop. But for now, let's focus on that offset. So let me open that up in the memory view. So that's my offset right there. And I told you that we have the history of all memory accesses in the trace. So it's super easy for me to just say, okay, open the history and show me everything that happened there. And this is the current access. This is a read. And so that's the previous one. The previous access is a write. So I can just double click there and it'll take me to that write. So I am placing a memory breakpoint and then going backwards until I hit it. So that was just a very easy way to say who wrote that. And what I have here, I see that I am seeing RDX from there. So, I see that the value comes from RDX. That's pretty interesting. But RDX is not super clear where it's coming from. So I would have to look into the code and locate RDX and do that same thing manually, going backwards a couple of times until I find the source and, I get more information about what's going on. But we do have a tool to do that automatically, and it's called the taint analysis. This is what I've been telling you about earlier. So instead of doing that manually, I'll ask the taint to do that for me. From current transition backwards to the start of the trace, taint that, and give me answers. Before I do that, I want to just show you, there we go. I just want to make a graph of what it is going to happen here. So right now I'm there. I have something observable, which I'm interested in, and that does something. And I'm interested about where it's coming from. So I'm going to get information about the data flow, where it's been going, what it's been going through, although I don't really care which register it is, but rather what functions have been moving that value around. And I will eventually find its source. And maybe that will give me some information. So that's a start. And once I have that, I can also taint that same thing forward. And instead of following just that branch, that source might have been copied over to somewhere else. And so I'll get new answers about other copies that might exist in my program. And maybe those copies have other children. And maybe those will yield new locations of interest. So really following the data flow both ways really helps you build that map of what data is being manipulated, where it's going, what's happening to it. And it's important to realize that the taint follows the flow, even if the value changes. It's not just, we're not just going to follow copies, but like if I have a source and then this is added to something else, like plus 10, then that copy is plus 10, but it's still counted as tainted value. So really, it's not just a copy, but children of that value that depends on that will also get tainted. And that will give us a lot of information. And this is what we are going to see in the taint widget right here. So I'm tainting that backwards. And what I get is a list of moments where that value was moved from one place to another. So there I see it was moved from that memory location back to RDX. So this is what we found manually using the memory history function. But then that same RDX comes from another memory value. And it's a copy, so it's not modified so far. And I can move all the way back, almost all the way back to that buffer. And if I open that buffer in my memory view and scroll up a little bit, you'll see that this is a PE file. Okay, so we have the usual MZ header there, and my value is E7FF. So what I just did there was I was inside the kernel and I was able to get an answer about where an offset was coming from just absolutely instantly. And I thought that this offset was probably built somehow, and maybe there was a bug in that in the building of that offset, and that was the cause of my crash. But actually, that offset was not built; it was just read straight from the file. So that's a very interesting piece of information right there. Again, if you have questions on it, otherwise I'll just keep going. So yeah, this is like the thing we can do in REVEN is get super quick answers about that. And that taint works through everything. Like if you have multiple processes talking to each other, they will talk to each other through the kernel. And since we have access to the kernel code, the taint will be able to follow data from one process to another super easily, because the taint is the trace is a consistent whole. We have all the code manipulating the data, including the kernel. So the taint can just follow that through. And if you push something to a name pipe and it's received somewhere and it crashes that other process, it'll be super easy to trace it back to the initial process. As long as everything stays on the same machine, it's very easy to follow. And when it's coming from the outside, like from a network packet, then we have ways to do that. And if we have time, we'll have a look at that as well. You can generate a pickup trace from a trace, and get that information and use that information to infer things about your trace. So really, that taint is I don't know. It's super powerful, I think, and it's really one of the main things people do all the time using REVEN. But REVEN is not everything, and at that point, I suspect I have a file there, and obviously this is probably my POC file which I uploaded to the virtual machine, but I'm not sure of that. And if I want to answer that, it's not super clear from a REVEN trace how I could do that. But I can use other tools, namely here what we're going to use is WinDebug. So what I have there is a WinDebug connected to the trace through a bridge program that we provide. That bridge on one side connects to the trace, and on the other side presents an interface that WinDebug knows how to talk to. And WinDebug thinks it is connected to a live running virtual machine. For those of you who are not familiar with that, it's capable of just using, the Windows kernel is capable of providing an outside WinDebug interface. And so WinDebug from the outside can break the machine from the kernel level and get a lot of information from there. And so this is the mode we're in. WinDebug is in kernel debug mode. And but instead of being connected to a real machine, it's actually connected to a trace. So that means I can point it at any moment of my trace, it's going to work. And what I had there is my WinDebug connected to that trace at a certain moment in time. And the moment is actually the start of that call. If you look at the arguments, and because you can get those functions are documented, you'll see that verify image header works on a buffer, the buffer that we saw there, but that's not super easy to see what that buffer is connected to. Although that second call here is actually taking a file object as argument. And so that's easier for me to get an answer about a file object. So that's what we're going to do. My WinDebug is connected at that moment in time. You see it's there, so that's my function start and I push a couple of things. And so what I'm going to do there is do bang object RCX, and RCX contains the first argument, so the file object, and you see that, yeah, it can tell, yeah, this is the POC file. Okay, so I know exactly what I'm dealing with, and I'm able to, yeah, get information from WinDebug. I can also use WinDebug as a navigation tool if I need to for some reason. Like if I was to synchronize my view, is it the right one? WinDebug 2. Okay, so I synchronize Axion, so our GUI to WinDebug, and I can just step into. So I can use that to navigate in my trace and, you know, move back and forth between the two if I have to. I can also just say, yeah, never mind, I need you to go somewhere else. So let's say I want to go back to that function. I'll just copy and paste that transition number and say, yeah, start again, and it's back there. So I can move backwards manually or move forward using the regular navigation tools in WinDebug. And yeah, I can, you know, so I can do whatever I want with that, and a lot of feature unlocked just by having that tool connecting to the trace. We support also breakpoints. So if you have custom tools that you know, are used to breakpoints and do actions on certain breakpoints, it's going to work. So yeah, we really made sure that we, you know, we handle that properly. So yeah, so going back to my use case here, if I let me go back to where I was, I have an offset, I know which file it is, and I know it's read and never touched, or at least it's not computed in any way, so that's not where the bug is. I've been telling you about the taint. This looks like that. So at that point, I am here. I found the source, and I know that causes a crash. But what I don't know is whether this value is checked or not. So what I'm going to do is I'm going to taint that forward. And actually, things that will get tainted are flags when the value is checked. When you do a comparison on that value, then the flag output will depend on the value. So the flag output will be tainted. It means that every time I'll see in my result that flag appears, it means that the value is being compared. And that helps me locate new locations of interest. So let's do that. I'm here. I'll copy the address range there. I'll taint that from there forward, taint. And what do I have? Yeah, I have first result, some flags tainted. What it is, it's comparing the value against 0. So it's more like a, yeah, check that it's not null. So I'm not too interested in that. And at that point, okay, I have the same thing here, I guess. Yeah, test EDX, okay. And I see that EDX is E7FF again. And then I have something more interesting, like I'm comparing about against something that might be an upper limit. So maybe this is a location of interest, and maybe there's a bug in there, like the upper limit is way too high, or it's coming from something else. And I want to understand the code, and I want to understand more context about what the code is doing here and what it might be doing in other cases. And since all I have here is a trace, of course, I wish I had the static view at that point. So that's where the integration with IDA and GitHub comes in, although we're seeing it running in IDA here. I have the same taint running here, and that's the location we were seeing earlier. And what I have here is we are able to synchronize IDA's current view onto what is currently selected in our GUI in REVEN, so that you could combine the two and again have both the dynamic and the static context always in sync, and that might help you, you know, analyze things further. And really the idea is that this time what you will get is not a straight answer, but rather a set of locations that you need to dig into more. And in that situation, REVEN helps you just, yeah, discover things, at the same time discover new areas of interest, but narrow down what you need to analyze, because in that case there are only a few set of things that were executed. So, you know, there's no other bug anywhere. I have a question on the chat. What's the size of the replay file? For that particular trace, let me look. It's not that big for that trace. Traces, so there are two different things that you need to, yeah, the highlights, okay, I'll get back to the highlights. There are two different things when we talk about trace size. First, the recording without the indexes. The recordings are honestly pretty small. They are anywhere between a gigabytes to 2 gigabytes. Or, I do have the recording that we made earlier is only 800 megabytes. And that's mostly dependent on how much RAM the virtual machine has. Then we create indexes, and that's where we need more disk space. And for the trace we're looking at, which is 200 million instruction, the trace is about 10 gigabytes large. So as said, this is actually a normal size trace. 200 million, 500 million instructions are normally sized traces. So anywhere between 10 to 20 gigabytes is regular traces, and the sky's the limit. For billions and billions of instruction, you could go up to terabytes of replay size. And I've seen a customer do, I think my personal record is 1.5 terabyte and I don't remember exactly how big the trace was, but it's pretty huge. But it just works because everything is properly indexed. So and as long as you don't need to extract information for every single instruction, which you usually don't, everything goes fine. About the highlights that we saw, what we see here is actually the coverage of the trace that we extracted. So this is something different. We created a proof of concept to evaluate whether this was possible. So it absolutely is, although it's not part of the product yet. So this is a work in progress. We can extract coverage from a trace, limited to a process or to a binary or whatever, and then import that coverage into Lighthouse, which is an IDA plugin. And this is what we're seeing here. We see the coverage from, it's here. This is the coverage from Lighthouse, which tells me, which function were executed there. So here, I think it's very interesting because it helps me see what exactly was, it's dynamic information pushed into IDA. Although obviously, if I had stepped multiple times in that same code, I would have multiple coverage overlapping each other. But that's the point of coverage. So yeah, you can extract coverage from a trace, and that could help you maybe do comparison or stuff like that. I see another question popping up. So yeah, while you're writing your question, so this highlight is the kernel coverage. Yeah, this is from there I extracted coverage for, I think, for the explorer.exe process. And that kernel code executes in the context of that process. So I got the coverage there. Or maybe I just recorded everything. I don't remember exactly. It doesn't matter too much because the trace here is very located on explorer.exe. And yeah, this is the kernel coverage anyway, because again, we have access to everything, so we can just extract coverage for anything that runs on the virtual machine, no matter what the ring it's running in. That's no issue for where we are at. Okay, so the bug we have there is actually the output of a fuzzer. So this was a bug published by Project Zero, maybe last year or the year before. And when we started analyzing that, I said we at Tetrane, because I didn't myself do the analysis for that. We had identified a couple of mutations that were necessary for the crash to occur. Okay, I think there were like 4. And we were able to understand 3 of these mutations, what their effects was, but one was a tougher nut to crack. So what my colleague did here, he reverted the mutation from the POC file, so the POC did not cause a crash, and he recorded the same operation he did for the crash, but this time with the mutation reverted. So on the left, what we have is a trace that does not crash with that mutation reverted. Okay, so if we go to the end, we see there's no crash. And to the right is the same trace as before, which crashes. And from there, we'll try to extract differences between the 2 traces to see what's different. So there are a couple of ways to go when we're talking about comparing traces. And because it's always going to depend on exactly what you want to do. But in that case, we'll do something very simple, but very straightforward. Not simple, but very straightforward. And we'll still get a lot of result, a very interesting result, at least a very good hedge. And if we look at the backtrace, again, I'm pretty sure that my bug isn't in memcopy, so I'm not interested in that. But the first function right there is mi relocate image. So we'll start diffing the instructions of mi relocate image call between the two traces. So I need to find it in the other trace, mi relocate image. Okay, luckily I have a single call to that, so that's going to be easy. And then I'll head over to a Python script which simply connects to trace A, trace B, extract instruction one by one and compares them. So I ran it, trace A, trace B, and I had given it the proper starting point, which we see here, 65 million and 42 million and 49 millions, and it found a first difference. So let's head to that first difference. No, I can't because the copy paste is broken again. Yeah, no copy paste today. So let's do that manually. 65, 553, 5171. Okay, to the left, and there, what I have here, 49. There we go. So what we have there is the first instruction that's different, and that's because I took a different branch there for that jump, because that's like on one side is 0 and on the right is actually 1. So that's my first difference, and from there I can start maybe tainting that flag backwards and look at the differences in the taint. And what it's going to do is it's going to give me a hint that some piece of code is not executed on one of those traces, and I can see why. Again, there's a difference in the flag. I can taint that backward, and yeah, just moving my way manually backwards, trying to understand what's going on. I quickly reach up the final mutation, the fourth mutation that I could not understand. So I'm able to fairly easily build a view of what's happening, what the differences are, and so build an understanding of what the mutation does for that file. So that's one way of approaching diffing. Another one is diffing dead results. This is something we're going to do next week in the lab. A third way we could approach tainting would be extracting ltrace calls. By ltrace, I mean library calls made by a binary, and then make a diff of that. So I can show you an example of that on a different trace. What I have on that different set of traces is a completely different use case. I was interested in seeing the differences between two runs of SVC hosts, which I renamed so that I could have a separate process, with or without the -p argument. And I was interested in seeing the differences between the two, because that argument, as far as I know, isn't documented. So I did that, and then I extracted the library calls from the binary called ABC host in my trace. Notice that this ltrace tool that we provide as a Python tool, but it's really something that's that we provide as a feature, also extract arguments. This is the first time we've started working on that kind of thing, where we can extract argument because we have a different source for information, because PDBs usually don't contain that. So it makes for a very readable trace, because you get the strings that are part of the arguments, you get the values, you get everything. Though it makes a super high level view of what's going on in the process. And there, it's super easy for me to compare the two things. Notice that I ignored values and things that might change between the two traces, but that's the only thing I did. I just extracted both traces. I did not have any intelligence of what was going on there. And super quick, it will yield that, there were a couple of calls made here that were not made on the trace without that argument. And while I could probably reproduce that with other tools in the live running system, the interest here is, first of all, it works in kernel land. And also, since I have the transition number, I can go back to the trace there with the -p argument and try to understand what the conditions are for that to run this -p, but maybe there's something else. In that case, we also need a certain registry key for that to be actually valid, or maybe there are other things that are not activated on my machine and I don't know about. So again, from there you can use that as a starting point in your trace to get more information and crack your case. So those were the things about trace diffing. You could always find new ways to do that, but really the idea is extract information and compare information from the two traces. That's one of the other things you could do with REVEN. Okay, again, if you have questions, don't hesitate. Otherwise, I'll keep forward. I'll keep going. We have a couple of minutes left, so that's good. What did I say we would have a look at? I told you we would look at integration, third-party tool. We did that. Tainting, we did that. Python API. We do have a Python API, and we integrate with Jupyter, which is a REPL environment that makes it easy to develop and discover the API mostly. So you can either run your Python script as Python scripts, and you can run them on the server, you can run them on your Windows machine, and but you can also do that through Jupyter, and that's a nice way to discover the API because you have completion there. It's all cells share context. It's very interesting, very nice way. We'll actually use Jupyter next week for the lab, so you'll get a grasp of that. But yeah, basically the API is super straightforward, and you get access to your trace, and then you make queries on your trace in a very similar fashion that you do in the GUI. So in that case, I'm looking at transition, first transition, which is our timestamp again, first transition, and displaying what symbols we have, and I can just do that, and it's going to work. So that can be used either as a way to filter things out from the trace, like if you want to process many calls, or you're looking for a certain call that returns a certain value. That's something that you need the API for. So yes, simple-ish things like that. So those are the first use cases that we cover. But also the API, since it can access the taint results and all of that, you can build complex heuristics with it. And we started publishing recently more complex heuristics to discover vulnerabilities in your trace, like uninitialized memory, I think, and most importantly, use after freeze. This was the first one that we published. So you could have a script that will get your trace and start doing taints, look for allocators, and get some intelligence there, and try do a lot of that automatically on the trace. So that's the API. Of course, we have a documentation on the web, so you can start looking at it if you're interested. Tetrane.com. That's our documentation. Okay, that's our documentation right there. So you can have a look at both the product documentation and the API, Python API here. You get, that's the installation. But you'll get, there we go. You'll get a quick start guide if you're interested in how it's meant to be used, and that's very easy for you to get through first. So I said I would talk about Python API, and since we have 5 more minutes, I can also get through maybe at a small malware example. And this one is interesting because it also talks about how to connect things with Wireshark. So let's take a minute and have a look at a third example, which is right here. Yeah, here we are. So completely different use case. This time what I have is a malware in the form of a DLL that expects to be loaded in explorer.exe. So that's probably already something that I extracted from something else. And what I did was make a binary called explorer.exe that would load the DLL, wait for 60 seconds, and then close the DLL. So the result of that is a trace so you can see it in the frame buffer. You can see my command line there. I did that, and towards the end of the trace, it waited for 60 seconds and then freed the library. Thank you, Quentin, for the links to the documentation in the chat. So that's what I have, and nothing super obvious happens. So I need external data to get inside that trace, like to get an entry point in that trace. So that's the output information I'm going to use in that case. I'm able to extract a PCAP file from a trace. So obviously, I could also simply record the network activity while I'm recording the trace itself, but then I wouldn't be able to connect data to the trace easily. Whereas here, since I extracted from the actual trace, I'm capable of saying, yeah, this is that buffer exists at that moment in time at that location. And that's what I have here. I have a packet there, which is suspicious because it's making a query there to google.com. And I'm pretty sure that /switch/article is not a valid google.com URL. So I'm interested in that packet. And the way I'll be using to link it to the trace is by looking at the output log of the script. In that case, it's saying, yeah, that transition, 4260, it's in that buffer. It's actually split in two buffers, but the one I'm interested in is that one. So I'll copy that over and towards Axial, and I'll open that location, and I can't because I don't have my buffer. Thank you. I'm sorry, the copy paste just stopped working on that session. I tried to fix it a couple of times, but it didn't work. So bear with me while I just type in the values. So 23, 95, 64 to 395, 64, I said, to 60. Okay, that's the proper location. And the buffer is this time is 4Fs. E0876F683200. Hopefully that's right. Yes, that's right. Okay, so I do have my packet there. Normal. So I do have my packet there, and I'm interested in seeing where the data is coming from, just to find my malware, find the program that sorted that. So that's a packet that's going outside of my machine, and I suspect my malware sent it. So I want to find the code of my malware that sends that or that builds that URL. But I am right there inside my kernel. That's how the script works. That's how the pcap extraction works. It works at the kernel level. So I'll link that back to my program, and I'll do that quickly because we're slowly running out of time. So let's do that. Data analysis, same thing. I think you got the idea. Take that, and I'll jump through all the results super quick and land there. And so those are all data flow. All of this is data flow. Values moving from one place to another. So you see that's quite a lot. And if I had to do that manually, that would have been a pain. But automatically, I'm able to link to a certain location in the Pogodown DLL. And you see it's just right, very close to the start. And this is actually the deobfuscation routine for strings stored in the malware. So that switch word was a string obfuscated, it got deobfuscated and then happened to the URL, and it ended up in the packet that was sent. And I was able to make that connection backwards just instantly by using the taint. And it went through the kernel, it went through my program, it went through the drivers, all that automatically. So that's, again, one of the, an illustration of what REVEN can do with big traces and just tools on top of that to extract data and extract information as quick as possible. Can REVEN run on the virtual machine? Quentin is answering that. You probably want to run that on actual hardware because of disk limit, the disk requirements. We're required to have pretty fast disks and connecting. So yeah, we don't support running it under a virtual machine. Yeah, I agree. In practice, it could work with nested virtualization, but that's probably not going to be a super good idea. And so we recommend really having proper hardware for running REVEN. AMD CPU and Intel CPU both work, although if you focus on QEMU recordings, both will work. And if you're interested in VirtualBox recording, which is again a kind of a very specific use case, you will be limited to Intel CPUs. But most of the for 99% of the use cases, both CPU are going to work. No, REVEN cannot run on a Windows host system, although through again, let's say virtualization, you could probably get something running. But again, disk requirements, we need pretty fast disks so that the experience is nice. And so we recommend running that on hardware. So we'll keep taking questions for the next maybe half hour if you're for people who keep having questions. So we made sure we'd be there if you need to, but otherwise this is the end of the demonstration. Hopefully you get a good idea what's going on there. what the project is, what we do, and if you're interested, next week we will be having an actual workshop. So you'll get access to the GUI that we saw and Jupyter notebooks as well. You'll be able to work through an introductory exercise, so you get your hands, used to how it works, and then we will dive into kernel land and kernel CVE. And don't worry, you don't need a lot of context. If you're mostly a Linux guy or you're not very much into kernel, don't be afraid. The exercises are super guided. And as you see, kernel code is just code. So there's nothing super involved there. And we'll get to some pretty interesting results. So stay tuned for next week. We will be available at the same time. So it's 5 p.m. Paris time. Yeah, hopefully I'll see you there. And in the meantime, enjoy your weekend. And I hope I got you excited about the product. And again, we'll stay on the chat for further questions. Okay. Bye, everyone.